This is a pericyclic gearbox consisting of just 4 bevel gears, and its biggest difference from conventional gears is clearly this weird wobbling motion, which provides extremely high gear ratios. This one, for example, here has about a 41 gear ratio, and see, it's super slim and pretty compact, but still not an insanely high gear ratio. You could achieve this with a worm gear too, and it would be quite compact. Now here we have also got just 4 gears, but this one has a 409 gear ratio. Hard to believe, right? There's a 409 times difference in speed and torque between the input and output. Look, even though I'm cranking the handle fast, the output shaft barely moves. It's super slow. By the way, I'm sure you are thinking this gearbox will vibrate like crazy, which as you can see, it really is. Look, at high speeds, it's wobbling so fast, it's called mutation by the way, and this unbalance kinda tears it apart, destroys it. But luckily, there's a pretty neat solution to this. Basically you add another set of gears to it, and it sort of balances out this motion. By the way, there is no extra mechanism in the system for this nutational movement. It's just that as the shaft rotates, the gear continuously moves up and down, and the source of this is the inclined surface on the shaft. I was able to machine this inclined surface on the lathe, but it was a bit complicated, and getting a nice surface finish wasn't easy, so I basically combined a straight shaft with a certain nutation angle with an inclined shaft, and 3D printed it. I then screwed this yellow gear consisting of these two parts and placed it on the inclined surface with bearings. Look, when the shaft is in this position, this point is up, so the gear is facing upward. As the shaft rotates, this point comes down, and now the gear is facing downward. In this way, as the shaft rotates, instead of rotating at the same speed as the shaft, the gear makes a nutational movement. By the way, there is no rigid torque connection between the yellow gear and the shaft, so to provide the necessary torque to the system, a reaction gear is added. You turn the input shaft, the yellow gear makes nutational motion, engages with the reaction gear at the back, takes the required reaction force, and thus drives the output gear. If I release the reaction gear, by the way, the gear ratio is broken. See, all three start rotating at the same speed, like a clutch. And if I hold the output gear, the reaction gear rotates in the opposite direction. By the way, there is generally a difference of 1 or 2 teeth between the mating gears in the gearbox. When there is a difference of 1 tooth, a gear disengages from one slot, passes a tooth and re-engages to the slot next to it. And a 2-tooth difference causes it to skip 2 steps. So when you turn the input shaft, the yellow gear and the gear in front of it connected to it rotate 2 steps backward. Then the interaction between the front gear and the orange output gear rotates the output gear 1 step forward this time. As a result, for one full rotation of the shaft at 360 degrees, the orange output gear only rotates 8.5 degrees, and this roughly translates to a gear ratio of about 41 times. And you see, while the input shaft is rotating around 180 rpm, the output is indeed extremely slow, just 4 revolutions. By the way, I made another version of this and got a transparent cover made by GLC PCB so I could see what's happening while it's working. This was produced using GLC PCB CNC services. It looks pretty good honestly. And let's see if it's back drivable. I can turn it easily from here, but from here... No, I can't turn it. It's like stuck. You know what I mean. It's not back drivable. The process is very simple. Upload your design, choose the material, options include aluminum, copper or plastic, and within a few hours you get a code. They made and shipped the cover in just 3 days, which was quite fast and smooth. GLC PCB has mid-year sales going on right now, so if you need PCBs, 3D printing or CNC services, it's a great time. For example, besides resin or nylon prints, they offer SLM 3D printing, which lets you print in stainless steel. They create the model by melting steel powder and results in genuinely solid steel. Alright, this is the one with a 409 gear ratio. Okay, let's turn it. Is it working? I can't tell, it's moving. It's really slow. And for just one full rotation of the output shaft, I would need to turn this handle 409 times. How slowly it's turning. So what's happening here right now? The wobbling gear rotates one step forward at the front, but before that it also rotates one step backward at the rear. So in total, when the input shaft makes one full turn, it rotates a very small amount, just as much as the difference between these two movements. This gearbox naturally generates very high tooth forces even with small input torques, due to the extremely high gear ratios it provides. If I were applying 1 Nm with this motor right now, I would have obtained around 400 Nm of torque at the output, which, as you can imagine, is quite high. And notice, this happens in just one stage. So how can the gear teeth withstand these high torques? So another great thing about this gearbox, for example, in a spur gear, during engagement, only one tooth is in contact. So all the load is concentrated on that single tooth. But in this gearbox, look, during engagement, many teeth are in contact. This means that the torque load will be shared by all the teeth in contact, resulting in smoothly transmit high torques and also quieter operation. The movement of the gearbox, as you can see, is a bit unstable, and this unfortunately doesn't allow high speeds. Right now the input is around 600 RPM and look how it's vibrating. In slow motion though, you can see that the yellow gear is actually rotating quite slowly compared to the input shaft. The problem here is the rotational motion it's making, which as you can see is quite fast and at the same frequency as the input shaft. Let's increase the speed to around 1500 RPM. And the gearbox is practically walking. When I increase the speed even more, first the screws start to loosen and then the whole gearbox starts to fall apart. The main reason for this is the fluctuating axial forces caused by the unbalance of the yellow gear. This motion creates gyroscopic moments that act on the gearbox housing along the shaft axis, and their effects can sometimes be greater than the meshing forces. The simplest solution is probably not to operate at high speeds. To completely eliminate this, an identical gear unit is added to the end of the gear unit, which balances the system. However, this has a few drawbacks. As you can see, getting output from the gearbox becomes a bit more complicated, so I added a spur gear in the middle. Moreover, the required number of gears, bearings, is now doubled due to the mirroring, and naturally the gearbox has become larger and heavier. I 3D printed all of these. By the way, I'll add the STL files of all the designs in the description, so you can print and tinker with them. Alright, let's turn it. It has got a very smooth rotation, doesn't it? Kind of relaxing. But honestly, I don't feel anything different from the previous version. It still feels a bit unstable. Anyway, look, this is the first pericyclic unit and this is the mirrored one. Since the shaft is one piece, I can drive both with this handle, and because I set them in opposite positions, their rotational movements are in opposite directions, you see, which cancels out the axial unbalances. The overall gear ratio of the system is the same as a single unit, about 41, it hasn't changed. Now let's add the other counter gear. Here the torque will decrease by 1.5 times and the speed will increase by 1.5 times. Let's give it a turn. Now with this handle I'm turning, which is the input shaft, there's about a 27 gear ratio between this and the aluminum extrusion output. Let's increase the speed a bit. Look at them spin. Around 1000 RPM and everything seems fine. It's going well, I think. There is still some vibration, but it's not because of the gears. check this out, the yellow gears are rotating so fast that they just appear to be spinning, but they are actually rotating at an extremely high speed. It's much better than before, and the gearbox as it is now is more reliable and we can get extremely high torque from it. It's just a bit too noisy, but of course we can't expect it to be as quiet as a magnetic gearbox I made before. By the way, a non-contact magnetic gearbox is really interesting. If you haven't seen it, you should definitely check it out. Now I was intending to lift a few real objects, but you see, since I designed the gearbox more as a model, this weak housing design doesn't really allow for a significant load. It flexes sideways under load, causing the gears to skip. The same thing happened with the other design, by the way. But if I press it like this from the sides, it works just fine. No skipping gears, and it's really powerful. It just needs a solid casing. And now I remember, I made a version like this too. Let's give it a try. That's all I have to say about these gears. Do you think they are useful or just unnecessary? Thanks for watching. If you liked it, please subscribe and check out my other videos.